Far beyond the faint blue glow of Earth, past the icy fringes of our solar system and into the glittering abyss of deep space, lies the constellation Leo. To the naked eye, it's just a cluster of ancient stars, but hidden within its reach, 124 light years from our world, a discovery has emerged that may forever change the human story. In the cold, silent void, the James Webb Space Telescope has fixed its gaze on a planet bathed in alien starlight. What it found was not just another distant world, but a place where the temperature hovers at a steady, life-friendly 120 degrees Fahrenheit, swaddled in an atmosphere alive with the chemical heartbeat of biology. This is not a speculative whisper or a hopeful anomaly. Scientists are 99.7% certain. If they are correct, we have stumbled upon something greater than we ever dared imagine. A planet more hospitable than Earth itself, teeming with life beneath alien skies. It began, quietly, almost mundanely, on a Tuesday morning in December. Across the world, people went about their routines, coffee brewing, traffic humming, unaware that the most profound message humanity had ever received was quietly arriving on a stream of invisible light. At Cambridge University, astrophysicist Niku Madhusudan sat before a wall of data, terabytes of information, each line representing infrared light that had traveled for over a century across the void, poured in from humanity's most powerful instrument in space. These photons, born in the glow of a distant red dwarf star, had crossed the gulfs of time and space just to be caught by Webb's golden mirrors. And there, buried in the spectral code, was a signal that made his hands tremble. It wasn't just water vapor. It wasn't just methane or carbon dioxide, those familiar gases that tease the possibility of habitability. It was dimethyl sulfide, DMS, a molecule that on Earth is produced exclusively by living organisms, especially tiny plankton drifting through our oceans. This was no faint trace. It was a signal strong enough to be undeniable. The odds of an error were vanishingly small, less than 3 in 1,000. In the field of astronomy, where certainty is rare and new claims are often dismantled within months, such confidence is almost unheard of. For Madhusudan, the realization hit with physical force. If this was real, then in one stroke, humanity's centuries of cosmic loneliness would end. The world in question is K2-18b, a so-called super-Earth, about 2.6 times the radius of our planet and 8.6 times its mass, orbiting quietly in the habitable zone of its cool, steady red dwarf star. But the phrase habitable zone doesn't do it justice. K2-18b is wrapped in a thick, hydrogen-rich atmosphere, far denser than our own. Instead of stripping away heat, it traps it, redistributing warmth so evenly that the night side, forever turned away from its star, still cradles liquid water. The oceans, if they exist, could stretch for thousands of miles under skies tinted in colors no human eye has seen. What stunned scientists was not just the temperature, a balmy 120 degrees Fahrenheit, comfortable for a wide range of life, but the stability. On Earth, such heat would trigger violent weather and evaporation. Here, the atmosphere acts as a perfect thermal regulator, like a planet-wide greenhouse fine-tuned for life. The hydrogen blanket insulates without suffocating, allowing water to remain liquid across vast stretches of the planet's surface. For months, Madhusudan's team had been watching, timing every transit of K2-18b as it passed in front of its star. Each time, Webb's instruments would detect the starlight filtering through the planet's atmosphere, breaking it into a spectrum of colors and chemical fingerprints. First came the unmistakable signature of water vapor, then methane, then carbon dioxide. Each finding strengthened the case for habitability. But DMS was different. On Earth, the only known source of this gas is biology itself. Detecting it in the atmosphere of a planet more than 100 light-years away was like spotting a neon sign blinking, "Life exists here," across the darkness of space. If true, the discovery would ripple through every culture, religion, and philosophy. The question, "Are we alone?" would be answered at last. Humanity would know that somewhere, under alien clouds, life stirs, breathes, and shapes its environment. And K2218b, far from being a pale copy of Earth, might be an improvement. Its star, cooler and smaller than our Sun, will burn steadily for trillions of years, unimaginably longer than our Sun's remaining lifespan. Where Earth faces a distant but inevitable destruction, life on K218b could flourish for eons beyond. Count. This planet's gravity, nearly 3 times that of Earth, would make movement difficult for us. A 150-pound human would weigh more than 400 pounds there. Yet that same gravity is a gift, holding the atmosphere in place for billions of years. Without it, gases would bleed into space, as they once did on Mars. The air itself is alien, dominated by hydrogen and helium rather than the oxygen and nitrogen we breathe. On Earth, hydrogen is a trace element in the atmosphere. Here, it is the defining feature. But rather than smothering life, it creates conditions where heat is evenly distributed, ensuring that even the coldest regions remain within a range where liquid water, life's universal solvent, can persist. Even, more telling is what Webb did not detect: ammonia. In a lifeless hydrogen-rich atmosphere, ammonia would be abundant. Its absence suggests something is actively removing it, a hallmark of biological processes. Combined with the presence of methane, carbon dioxide, water vapor, and the powerful signal of DMS, the case becomes stronger with each analysis. And so this December morning will likely be remembered as the moment the boundaries of our reality shifted. For generations, we believed life would be found on an Earth twin, a rocky planet orbiting a sun-like star. K218b obliterates that assumption. It tells us that life may bloom under skies nothing like our own, on worlds once dismissed as uninhabitable. Red dwarfs, making up the majority of stars in our galaxy, are no longer just faint background lights. They are beacons, potential hosts to countless living worlds. Above all, the James Webb Space Telescope has proven itself more than an observatory. It is a time machine, an interstellar messenger, and a mirror showing us a universe far stranger and far more alive than we dared to hope. This is just the beginning of a story that will unravel not only the nature of life beyond Earth, but our own place in the cosmic order. Floating a staggering 1 million miles from Earth at a precise gravitational balance point known as Lagrange Point 2, the James Webb Space Telescope hangs in a realm of eternal twilight. Here, in this celestial outpost, the Sun, Earth, and Moon all remain in the same slice of sky, allowing Webb to maintain a constant position relative to our planet. It is a place of perpetual darkness, a sanctuary where sunlight never touches its instruments. Suspended in this void, Webb is shielded from the solar furnace by a sun shield the size of a tennis court, a 5-layer barrier thinner than a human hair, yet capable of blocking heat so effectively that its instruments are kept colder than the frozen surface of Pluto, colder, in fact, than liquid nitrogen. At the heart of this machine of wonders gleams its most striking feature: a 21-foot wide primary mirror, nearly 3 times the diameter of Hubble's, but size alone is not the true magic here. The mirror is made of 18 perfectly engineered hexagonal segments, each coated with a microscopically thin layer of pure gold, no thicker than a human hair's width, designed to maximize infrared reflectivity. Together, these segments form a single, precisely curved surface so flawlessly aligned that Webb can detect the feeble heat signature of a bumblebee on the moon. Infrared light, invisible to human eyes, is Webb's primary language. It is the light of heat, of dust-shrouded galaxies, of the faint atmospheres of alien worlds, and it is the single most important key to detecting life across the vast darkness of space. When a planet crosses in front of its parent star, a tiny fraction of starlight passes through the planet's atmosphere before traveling onward toward us. Each molecule in that atmosphere absorbs a very specific set of infrared wavelengths, leaving behind a fingerprint of life hidden in the starlight. Webb can detect these molecular fingerprints with a precision that borders on the impossible. To put the challenge into perspective, imagine trying to detect the faint green glimmer of a firefly hovering right next to a floodlight from 1,000 miles away. That's the scale of difficulty Webb faces when observing the star K2-18, which outshines its orbiting planet K2-18b by billions of times. And yet, Webb can isolate the faintest possible traces of infrared light from that planet's atmosphere, separating it from the blinding glare of its star with surgical precision. One of Webb's most remarkable tools in this pursuit is its coronagraph. Originally designed to block the overpowering light of stars so that fainter objects nearby can be revealed, this technology acts like an interstellar veil. Webb's onboard systems and advanced image processing algorithms work in unison to subtract starlight so effectively that only the delicate whisper of atmospheric molecules remains. It's like silencing the deafening roar of a jet engine so you can hear the gentle crackle of a match being lit in the distance. The discovery of dimethyl sulfide in the atmosphere of K2-18b demanded Webb to operate at the razor's edge of its capabilities. This molecule, on Earth produced almost entirely by living organisms, leaves behind such a faint signature that confirming its presence required months of repeated observations. Each exposure captured only a few precious photons, particles of light that had traveled 124 light-years through the cold vacuum of space, carrying with them the secrets of a living, breathing world. But Webb's triumph did not stop at detecting molecules. With an astonishing degree of accuracy, the telescope also measured the surface temperature of K2-18b, 120 degrees Fahrenheit. That's warm enough to allow liquid water to flow freely, yet cool enough to avoid boiling it away. This is not a rough estimate. Webb's readings are accurate to within just a few degrees across an unfathomable gulf of interstellar space. For exoplanet research, this is a precision record, one of the most exact environmental measurements ever made of a world beyond our solar system. Turning the raw data from Webb into these revelations requires computational power as extraordinary as the telescope itself. Artificial intelligence and machine learning algorithms sift through millions of readings, identifying patterns and anomalies too subtle for the human mind to catch. It is a marriage of human ingenuity and machine logic, a collaboration where science fiction has quietly become science fact. And then there is the number, 120 degrees. On Earth, it's the blistering heat of Death Valley at midday, the soothing warmth of a hot spring, the fever temperature of a human body fighting off illness. On K2 to 18b, it is the number that could define the destiny of life. Temperature is the cosmic gatekeeper of biology. Too cold and water freezes into lifeless ice. Too hot, and it evaporates into barren skies. The habitable zone, that narrow orbital band where liquid water can exist, is one of the rarest sweet spots in the universe. Earth happens to sit almost exactly in the center of our sun's habitable zone, a stroke of cosmic luck that has allowed life to thrive for billions of years. But K2-18b's perfect balance is no accident. It is the result of a delicate interplay between the gentle warmth of its red dwarf star and the insulating power of its thick, hydrogen-rich atmosphere. This atmosphere acts like a colossal planetary blanket, trapping just the right amount of heat. And because K2-18b is tidally locked, with one side eternally bathed in daylight and the other in endless night, this heat is redistributed with remarkable efficiency, keeping the entire planet within a life-friendly comfort zone. This stability is profound. On Earth, life must adapt to extremes, from scorching deserts to frozen tundras, from tropical humidity to polar dryness. Organisms evolve strategies to cope: migration, hibernation, metabolic changes. But on K2-18b, none of these. Survival tactics would be necessary. Here, life could pour all its energy into growth, reproduction, and innovation, unburdened by the seasonal hardships that shape our own biosphere. Even more astonishing, laboratory studies suggest that life can thrive at temperatures far higher than 120 degrees Celsius, up to around 250 degrees Celsius. At 120 degrees Celsius, chemical reactions within living cells can proceed with remarkable speed, fueling complex metabolisms while staying cool enough to protect delicate biomolecules. In other words, K2-18b is not just habitable. It might be more biologically comfortable than Earth itself. In a universe dominated by frozen wastelands and volcanic infernos, K2-18b stands out as a beacon of possibility. And at the heart of this revelation is a single extraordinary molecule: dimethyl sulfide. Its name may sound clinical, even forgettable, but to humanity it may one day be remembered as the first whisper from life beyond our world. When the James Webb Space Telescope locked onto the faint spectral whispers from K2-18b's atmosphere, it uncovered something the cosmos had never before surrendered to human eyes: a molecule with no known origin in lifeless chemistry. It was the calling card of life itself. That molecule was dimethyl sulfide. On Earth, dimethyl sulfide, DMS, is a subtle but powerful player in our planet's biosphere. It drifts invisibly from the sea into the sky, produced exclusively by living organisms. Microscopic phytoplankton, the drifting plants of our oceans, create it as a metabolic byproduct, releasing it into the air where it seeds clouds and alters weather patterns. Marine bacteria, certain species of algae, and even some terrestrial plants join in this quiet planetary-scale conversation between ocean and atmosphere. But nature's chemistry is strict. In every laboratory, in every volcanic plume, in every sterile reaction chamber humans have tested, no geological or non-living process has ever produced dimethyl sulfide. This exclusivity makes it a gold standard biosignature, far more decisive than oxygen, which can arise from sunlight breaking apart molecules, or methane, which seeps from volcanoes and hydrothermal vents without the help of life. Its chemical structure reads like a cryptogram of biology: sulfur atoms clasped to carbon-bound methyl groups, a union so intricate it demands specialized enzymes. On Earth, these enzymes are the handiwork of evolution's slow, deliberate craftsmanship, shaped over billions of years through the sulfur cycle that helps regulate our climate. To find such a molecule light years away is to glimpse indirectly the evolutionary ingenuity of alien life. What stunned scientists most was not just finding DMS on K2-18b, it was how much of it was there. Webb's measurements revealed concentrations so abundant they couldn't be explained by a lonely microbial foothold or scattered pockets of life. This was a biosphere on a planetary scale, a living world where biology wasn't just surviving, but actively rewriting atmospheric chemistry. To produce such a strong signal from 124 light-years away would require vast, thriving ecosystems. Oceans or landscapes teeming with organisms, pumping their invisible signature into the skies in quantities billions of times greater than a whisper from a few scattered microbes. This finding does more than point to alien life. It suggests that the basic blueprint of biology may be universal. If K2-18b's organisms are making dimethyl sulfide, they've likely evolved pathways parallel to life on Earth. Carbon, hydrogen, oxygen, nitrogen, and sulfur woven together in predictable patterns wherever chemistry gives birth to biology. Life, it seems, may follow the same rules across the universe. But bold claims demand ironclad proof, and Webb delivered it. When the raw data from K2-18b came back, astronomers braced themselves for ambiguity. Instead, the analysis spoke with astonishing clarity, a 99.7% probability that the DMS signal was real. In the conservative world of science, where probabilities are hedged and certainty is rare, this was a thunderclap. To put that in human terms, imagine flipping a coin 1,000 times and seeing it land on heads 997 times. The odds of that happening, by chance, are so infinitesimally small that it could not plausibly occur in the history of the universe. That's the level of statistical confidence Webb achieved, a solid 3 sigma detection. In physics and astronomy, 3 sigma isn't casual optimism. It's the threshold used to confirm the Higgs boson, verify gravitational waves, and record the most transformative discoveries in modern science. Reaching this certainty for an exoplanet's atmosphere pushed Webb to its extreme limits. The DMS signal was barely there, just a few parts per billion in the infrared spectrum. To catch it, Webb had to measure light's wavelengths with an accuracy of 1 part in 10 million, as if measuring the width of a human hair to the precision of a single atom. This wasn't a one-shot success. Over months, Webb's instruments revisited K2-18b, capturing the same molecular fingerprint at multiple infrared wavelengths. Each dataset was run through independent algorithms that chewed through millions of data points, hunting for systematic errors, contamination, or instrument artifacts. Every alternative, unknown chemistry, stray Earth-based interference, random noise, was tested and eliminated. What remained was the unshakable truth. Dimethyl sulfide, made by living things, drifting in the skies of an alien planet. And, if the molecule was shocking, the world beneath it was even more so. Beneath K2-18b's alien clouds, scientists believe lies an ocean unlike any in our solar system. A deep, global sea, not of pure water, but a hydrogen-rich brew under crushing pressures that would obliterate earthly life as we know it. Yet, paradoxically, this exotic ocean may be one of the most life-friendly environments in the known universe. K2-18b's thick hydrogen atmosphere doesn't simply hover above the water, it dissolves into it, creating a unique chemical blend. This hybrid ocean remains stable across a far wider range of temperatures and pressures than pure water ever could, buffering the world against the environmental extremes that make most planets hostile. The result is a liquid domain that could nurture life forms adapted to chemistry and physics utterly unlike our own, yet following the same universal rules that brought life to Earth. Here under alien skies, in a sea infused with hydrogen and mystery, something is breathing. And for the first time, humanity is not just imagining it, we have proof. The hydrogen-water blend on K2-18b is no ordinary ocean. It exists in a delicate, alien equilibrium, capable of remaining liquid from temperatures near freezing all the way up to an astonishing over 300 degrees, about 150 degrees C, a thermal range that on Earth would kill most known organisms instantly. Such an environment grants life a colossal playground of possibilities, spanning climates from the icy edges of polar seas to simmering near-boiling shallows. On our own planet, the deepest points of the ocean, like the Mariana Trench, are subjected to pressures over 1,000 times greater than at sea level, crushing anything that hasn't evolved extreme structural adaptations. But K2-18b's ocean cheats that deadly physics. The hydrogen dissolved in its waters acts as a pressure softener, preventing the overwhelming force of the depths from destroying delicate cellular structures. Even far beneath its surface, the ocean maintains conditions reminiscent of shallow coastal waters on Earth, an impossible luxury for deep-sea creatures here at home. Yet the real marvel of this hydrogen ocean is its potential to act as a planetary life support system for eons. One of the slow killers of worlds is atmospheric loss. Mars, once thought to have rivers and lakes, lost its atmosphere and became a frozen desert. Even Earth's protective blanket is leaking molecules into space every day, a slow countdown to sterility. But on K2-18b, the hydrogen ocean acts like a colossal backup reservoir. As hydrogen molecules escape into space, fresh ones bubble out from the ocean's depths, endlessly replenishing the atmosphere. This self-healing cycle could preserve the planet's climate not just for billions, but for trillions of years, longer than the current age of the universe itself. For life, hydrogen is more than a blanket. It can be fuel. On Earth, a handful of hardy microbes can metabolize hydrogen, extracting energy from it, but they live on the edge of scarcity. On K2-18b, hydrogen-breathing organisms might flourish in an abundance their earthly cousins could only dream of, inhaling the ocean itself as an energy source. And here's the mind-bending part. These life forms could be completely invisible to our most common detection methods. Earth scientists have long searched for life by looking for oxygen-rich atmospheres like ours. But what if the most dominant life elsewhere doesn't make oxygen at all? What if they leave behind chemical trails we barely recognize? The dimethyl sulfide already found may be just one signal among many in a symphony of alien biochemistry. The ocean's depth is another mystery that teases the imagination. Simulations suggest it might plunge hundreds of miles down, dwarfing Earth's deepest basins. Such a colossal volume of stable, life-supporting liquid could host ecosystems so vast and so diverse that they make Earth's biosphere look like a small island in comparison. With stable pressure, protective chemistry, and uninterrupted timescales for evolution, life here could have developed in directions entirely inaccessible to Earth's conditions. Above these waters, the sky tells its own story, one written in methane clouds, carbon crystals, and the glint of falling diamonds. Earth's atmosphere, a simple nitrogen-oxygen mix, feels almost primitive compared to the chemical artistry overhead on K2-18b. Methane drifts in rich swaths across the hydrogen sky. Carbon dioxide, more abundant here than in our air, mingles with methane and hydrogen in a complex, planet-wide chemical dance. Under the crushing pressures of the upper atmosphere, carbon atoms bind into crystalline diamonds, which glitter downward in constant gemstone showers. To us, they would be treasures. To life on K2-18b, they might be nothing more than common weather. Methane, though exotic in such abundance for Earth, is familiar in its origin. Here, it may be churned out in staggering amounts by living organisms, just as bacteria and animals produce it on our world. On Earth, methane vanishes quickly, broken down by sunlight and reactions in the air. Its persistence in K2-18b's atmosphere means something is constantly replacing it, and replacing it on a global scale. Even more intriguing is the possibility that life here breathes methane, using it the way we use oxygen, weaving it into their own alien energy cycles. The planet's red dwarf sun plays its part in shaping this strange world. K2-18b is tidally locked, one side forever bathed in its star's dim crimson glow, the other locked in eternal night. This could have been a recipe for climate disaster, but instead, it drives planet-spanning rivers of air. Heat, moisture, and chemical compounds surge from day to night, mixing the atmosphere into a planet-wide equilibrium. The hydrogen-rich air forms a protective barrier, shielding the surface from the violent stellar flares common to red dwarfs, radiation bursts that could sterilize other worlds. Perhaps most astonishingly, the chemistry of K2-18b's air hints that life here could be more advanced, or at least more diverse, than on Earth. In a place where diamonds fall like rain, where methane breathes through alien gills, and where oceans themselves act as both cradle and lung, evolution might have invented solutions to survival that Earth's biology has never imagined. And it all happens under the watchful light of a small, unassuming red dwarf, a star type that makes up nearly 3/4 of all stars in our galaxy. Unlike our sun, which will swell and die in a few billion years, red dwarfs burn slow and steady for trillions of years, granting worlds like K2-18b almost limitless time for life to grow, adapt, and thrive. In the vast, cold sweep of the Milky Way, these faint stars may be the true architects of life's abundance. They are the cosmic slow burners, red dwarf stars, small enough to fit comfortably in the category of stellar lightweights, often possessing less than half the mass of our sun. Yet, in the grand clockwork of the cosmos, they are the ultimate marathon runners. By sipping rather than gulping their nuclear fuel, these stars can keep their steady fires burning not for billions, but for up to 10 trillion years. To put that into perspective, if our sun's 10 billion-year lifespan were a single human lifetime, a red dwarf would be the ancient sage who outlives civilization after civilization, still standing when entire epochs have turned to dust. This staggering cosmic longevity changes the very rules of life's potential. On Earth, it took nearly 4 billion years for single-celled life to slowly, painfully evolve into the dazzling web of biodiversity we see today. If a planet like K2-18b has had even a fraction of those 10 trillion years under the steady gaze of its red dwarf sun, life there could have advanced to levels so intricate, so sophisticated, that Earth's biosphere might seem like a primitive prologue by comparison. Imagine civilizations with evolutionary head starts, measured not in centuries, but in entire galactic eras. The parent star, K2-18, is an outlier among its kind, unusually calm. Many red dwarfs are infamous for temperamental outbursts, unleashing stellar flares thousands of times more powerful than anything our sun produces. These eruptions can sear away planetary atmospheres, sterilize surfaces, and reduce promising worlds to lifeless wastelands. But K2-18 is what astronomers call a well-behaved red dwarf producing minimal flare activity. Its quiet nature allows its orbiting planets to maintain their atmospheres, shielding delicate ecosystems from the cosmic violence that dooms so many other worlds. Despite being smaller and cooler than our Sun, K2-18 still nurtures a Goldilocks zone, a narrow orbital belt where conditions are neither too hot nor too cold, but perfectly balanced for liquid water. K2-18b, with an orbital year lasting just 33 Earth days, circles its star at a distance far closer than Mercury lies to our Sun. Yet because the star is cooler, this intimate proximity delivers almost exactly the same amount of energy per square meter as Earth receives, a miraculous alignment that grants K2-18b its life-friendly temperatures. But here's the twist. Unlike Earth, which is racing toward its eventual destruction when our Sun swells into a red giant, K2-18b could bask in this perfect thermal equilibrium for trillions of years. That's an evolutionary sandbox so vast that the emergence of life, complexity, intelligence, and even civilizations might not just be possible, they might be inevitable. There's another peculiarity. K2-18b is tidally locked to its star, meaning one hemisphere basks in eternal daylight while the other sleeps forever in darkness. On most worlds, such an arrangement would create brutal temperature extremes, a scorched wasteland on one side, a frozen desert on the other. But K2-18b's dense, hydrogen-rich atmosphere works as a planetary heat pump, distributing warmth so effectively that both hemispheres remain hospitable. The result is a world of contrasts, a sunlit hemisphere glowing in perpetual dawn, and a night side bathed in starlit ice, each harboring entirely different habitats for life to adapt to. And then there's the distance, 124 light-years. Vast. Beyond comprehension, yet cosmically close. The light we see from K2-18b tonight began its journey when Teddy Roosevelt was President of the United States. Our fastest spacecraft would take over 2 million years to reach it. And yet, in the vast scale of the Milky Way, a galaxy over 100,000 light-years across, this world is practically a next-door neighbor. If the Milky Way were shrunk to the size of North America, Earth would be a grain of sand, and K2-18b another grain lying just the width of a small town away. Incredibly, from this distance, we can still read its atmospheric chemistry. The faint starlight passing through K2-18b's atmosphere carries with it the molecular fingerprints of its gases. That light travels across 124 years of interstellar emptiness before finally kissing the gold-plated mirrors of the James Webb Space Telescope. And what Webb reveals is extraordinary. Clear traces of dimethyl sulfide, a chemical on Earth produced almost exclusively by living organisms. This means that the breath of alien life, exhaled more than a century ago, is just now reaching our eyes. The strength of that signature is staggering. For it to be visible across such a gulf, the biological activity on K2-18b must be immense, not the quiet hum of a sparse ecosystem, but the planet-wide heartbeat of a thriving biosphere. We are detecting life not as a rare spark, but as a roaring bonfire. K2-18b's position also makes it a prime target for the telescopes of the future. While no spacecraft will reach it within human timescales, upcoming observatories like the extremely large telescope, with a mirror over 100 feet across, could parse its atmosphere molecule by molecule, uncovering dozens of potential biosignatures, and painting the first detailed portrait of life beyond Earth. And perhaps the most goosebump-inducing thought, The same 124-year gap works both ways. If intelligent life exists on K2-18b, they could be seeing Earth as it was in the early 20th century, their telescopes catching the first century of our radio broadcasts, our accidental hello to the stars. Somewhere on that world, perhaps a mind is looking back at us, wondering the same thing we are. Are we alone? Or have we just made first contact across the dark ocean between suns? The coronagraph's true genius lies in something deceptively simple yet astronomically challenging: its contrast ratio. In the case of K2-18b, that ratio is about 10 billion to 1. To grasp the enormity of this feat, picture standing on the far side of a continent, peering through a telescope and trying to pick out the flicker of a lone candle burning right beside the blinding glare of the brightest stadium lights during a championship night game. That's what the James Webb Space Telescope must accomplish every time it seeks a faint planet orbiting an overpowering star. And astonishingly, the coronagraph makes this once impossible task seem almost routine. But blotting out the starlight is only the first half of the battle. Once the glare is gone, another invisible enemy emerges: speckles. These are ghostly, pinpricks of false light, imperfections caused by minuscule irregularities in the telescope's optics. They mimic planets so convincingly that even trained astronomers can be fooled. To separate truth from illusion, Webb's onboard AI-driven algorithms work like detectives, examining every photon, comparing patterns in real time, and dismissing the imposters. This process is the computational equivalent of scanning millions of photographs at once, searching for a single specific face in a crowd the size of an entire city. All of this relies on Webb's ability to hold its aim with unthinkable precision. It must remain locked in position to within a few milliarc seconds. Imagine holding a laser steady enough to hit a dime on the moon. Any tremor, any whisper of movement could smear the data and erase months of planning. Yet the coronagraph does more than merely block and steady light. It reshapes it, employing a technique called wavefront correction. By continuously adjusting the path of incoming light at a microscopic scale, Webb creates near-perfect imaging conditions, revealing hidden worlds that would otherwise remain forever unseen. The technology that allowed us to see K2-18b is not an endpoint, but a dawn. Future telescopes will wield coronagraphs so advanced they could detect Earth-sized planets circling sun-like stars, unveiling dozens, perhaps hundreds, of potentially habitable worlds. And the impact is not merely technological, it's philosophical. Every faint planet we uncover is another reminder that the universe is not a sterile void, but a crowded cosmic neighborhood full of possibilities. When astronomers calculated K2-18b's mass, their results upended conventional wisdom about habitability. Weighing in at 8.6 times the mass of Earth, it sits between Earth and Saturn in scale. But unlike Saturn, it's not a barren gas giant. Evidence points to a vast water world, potentially more favorable for life than Earth itself. This challenges the long-held notion that our planet's size is the perfect Goldilocks for life. K2-18b's immense gravity, nearly 3 times Earth's, acts as a powerful guardian. It holds onto its atmosphere with unyielding strength, shielding it from the kind of atmospheric loss that left Mars a frozen desert. Even the fiercest flares from its host star would struggle to strip away its protective envelope. That same gravity also traps water with astonishing efficiency, preventing the slow escape of hydrogen into space and allowing oceans to endure for billions, perhaps trillions of years. Deep within, crushing pressures may have forged an ice-rich core surrounded by liquid oceans hundreds of miles deep, oceans so vast they could swallow all of Earth's waters many times over. In astronomical terms, K2-18b sits squarely in the super-Earth category, the sweet spot between rocky, worlds and gaseous mini-Neptunes. This position grants it the stability, atmospheric depth, and water reserves to support complex biospheres for timescales that dwarf our planets. Its colossal mass also means it retains heat far longer than Earth. While our planet's core will eventually cool and fall silent, K2-18b could remain geologically alive for longer than the current age of the universe, keeping its climate stable and its carbon cycle active. In other words, it's not just an Earth analog, it's Earth's bigger, stronger, longer-lived cousin. And then, there are worlds like the one circling CE Antel. Webb didn't detect this one directly. Instead, it spotted a telltale gap in the star's sprawling debris disk. These disks are the chaotic leftovers of planetary construction, icy shards, rocky fragments, and cosmic dust swirling in wide rings. When a planet takes shape within such a disk, it sweeps its orbit clean, leaving a crisp, unmistakable gap. The debris disk around CE Antel is particularly spectacular because, from our vantage point, we see it face on, like looking straight, down at a record spinning in space. This rare perspective reveals every structure in startling detail. 3 concentric rings of dust, each separated by gaps almost certainly carved by hidden planets. It's a silent, cosmic architecture, a portrait of worlds being born. When the James Webb Space Telescope turned its unparalleled infrared gaze toward the young star CE Antaeus, it uncovered something astonishing hidden within one of the disk's dark gaps, a faint, ghostly glow of infrared light. This was not the random flicker of dust or the interference of a background star. No, this was the unmistakable signature of a new world, a planet no one had ever seen before. It had been waiting there, cloaked in cosmic secrecy, concealed by the very material that had given birth to it. Astronomers soon confirmed the incredible truth. This object, now officially catalogued and christened, carries a mass comparable to Saturn, yet resides in an entirely different kind of environment. Rather than drifting far from its star like the gas giants of our own solar system, it orbits directly between the first and second concentric rings of CE Antaeus' glittering debris disk. And here's the eerie part. Its position was exactly where advanced simulations had predicted a planet must exist to explain the disk's unusual structure. Nature had placed it right on cue, as though following a cosmic blueprint. This find marks the dawn of a powerful new method of planetary discovery. Until now, we've largely found exoplanets through transits, waiting patiently for them to cross their stars' faces, or by detecting the subtle gravitational wobbles they induce. But Webb has proven we can read a planet's presence, in its absence, in the very gaps it carves through a dusty ring. This is the power of direct imaging, a technique that allows astronomers to detect and study planets that will never transit from Earth's viewpoint, vastly widening the universe of worlds we can observe. Yet the CE Antaeus planet is not a passive passenger on its cosmic route. The sharply defined rings of its debris disk betray a dynamic sculptor at work, as it sweeps through its orbital lane. The planet acts like a celestial architect, clearing vast corridors of dust and ice, compressing other material into tight, bright rings. It is shaping the very architecture of its stellar neighborhood. Even more enticing, Webb's infrared instruments measured the planet's temperature at around 120 degrees Celsius, about 49 degrees Celsius, a reading that tantalizingly overlaps with the range where liquid water could exist. This places it inside the star's habitable zone, though scientists caution it is far too early to declare it an ocean world. Its placement in the debris disk hints that it's still in its youth, perhaps still accumulating mass, still forging its final form. If so, we might be watching a world in its cosmic adolescence, one that has not yet settled into the atmospheric complexity of mature planets. The CE Antilles discovery is a reminder that planet formation is not ancient history. It is happening right now, across the galaxy, in countless star systems. With Webb's unmatched ability to peer through veils of dust, humanity can finally witness this process unfolding in real time. From chaotic rings of rubble to the first stable orbits of newborn worlds. We are not merely finding planets, we are watching them being born. But CE Antilles was just one chapter in a rapidly expanding story. As Webb continued its ambitious survey of nearby stars, a remarkable pattern began to emerge, one that may forever alter humanity's understanding of life in the cosmos. The galaxy is not sprinkled with a few rare habitable oases. It is teeming with them. Within a modest sphere of space just 200 light-years from Earth, astronomers have now identified more than 50 worlds showing credible signs of habitability. Some are super-Earths, like K2-18b. Others are rocky planets hugging the gentle warmth of red dwarf stars. Each represents a unique experiment in planetary design, with chemistry, atmosphere, and surface conditions unlike any other. The diversity is staggering. A few of these planets orbit close to their stars, protected by dense atmospheric blankets that trap warmth and keep oceans from evaporating, even in searing heat. Others dwell in the far reaches of their systems, sustained, not by sunlight but by internal heat and thick insulation. Some are cloaked in global ice sheets with secret oceans beneath, where alien ecosystems could thrive in eternal darkness. And this diversity extends to the stars themselves. Red dwarfs, by far the most common stars in the galaxy, can sustain habitable zones for trillions of years, offering life a near-infinite runway for evolution. Meanwhile, massive short-lived stars create brief but intense windows for rapid adaptation. The statistics are almost dizzying. If 50 promising planets exist within 200 light-years, then across the Milky Way's 400 billion stars, billions, perhaps tens of billions, of habitable worlds could be out there. The odds shift dramatically. Life may not be a rare cosmic accident, but a natural outcome of the universe's design. And on one of these worlds, K2-18b, the story turns truly extraordinary. Water, the universal solvent of life, is not scarce here. It is abundant beyond Earth's wildest imagination. Early Webb readings found water vapor saturating its thick atmosphere, a signature so strong it could only come from truly colossal oceans. To grasp the scale, consider Earth's oceans, about 350 million cubic miles of water, covering 70% of our surface with an average depth of just over 2 miles. On K2-18b, scientists suspect oceans that could be hundreds of miles deep, storing 1,000 times more water than all Earth's seas combined. At such depths, pressures would crush any terrestrial submarine, yet for alien life, these vast abyssal plains could be the perfect cradle, and this isn't just ordinary water. Mixed with atmospheric hydrogen, it forms a chemical cocktail that remains liquid over a far wider range of temperatures and pressures than pure H2O. It's a stable, enduring ocean, a planetary-scale incubator where life could arise and persist for eons. When scientists turned the James Webb Space Telescope's gaze toward K2-18b's hydrogen-rich oceans, they began to uncover a world so alien, yet so tantalizingly life-friendly, that it could rewrite the definition of habitability. This was not just about finding water. It was about discovering a planetary cauldron of chemical possibility, where the very nature of life might be rewritten. Imagine vast oceans infused not with the familiar chemistry of Earth's seas, but with a hydrogen-enriched elixir, capable of sustaining organisms that could literally breathe the water itself, extracting energy directly from dissolved gases. These would be creatures unlike anything in Earth's fossil record, thriving in a medium that is both their home and their fuel source. But perhaps the most astonishing aspect of K2-18b's oceans is not their exotic chemistry, it is their enduring stability. On Earth, our oceans are slowly escaping into space, molecule by molecule, as sunlight breaks water apart high in the atmosphere. Over billions of years, this trickle will dry our planet. But on K2-18b, immense gravity and a dense atmospheric blanket lock the water in place. Here, oceans could persist for trillions of years, granting life not just time to appear, but time beyond imagination to evolve. These oceans, kept at a balmy 120 degrees, 49 degrees, by a potent greenhouse effect, are not merely habitable. They are energetic accelerators of biology. Warm enough to speed up complex chemistry, yet cool enough to preserve fragile organic molecules, they are the perfect incubators for life. It's as if the entire planet is a giant, stable, life-calibrated oceanic greenhouse, fine-tuned by nature's hand. And the water does more than nurture life. It regulates it. By absorbing massive amounts of carbon dioxide from the atmosphere, K2-18b's oceans act as a planetary thermostat, stabilizing climate and chemistry over geological epochs. This balance, so critical for sustaining complexity, could allow alien ecosystems to flourish for eons without collapse. But oceans tell only part of the story. Webb's instruments captured something more profound: the planet's atmospheric fingerprint, etched into the starlight itself. As light from K2-18b's sun filters through its atmosphere, specific wavelengths are absorbed by gases, creating a spectral code that astronomers can read like cosmic DNA. This is no ordinary spectrum. Instead of the predictable stability of a dead world, K2-18b's atmosphere is in chemical disequilibrium, a volatile blend of gases that should not coexist unless something is constantly replenishing them. On Earth, that something is life. We maintain oxygen and methane together in our skies, even though they should naturally destroy each other, because living organisms produce them continuously. On K2-18b, the same kind of imbalance exists, but with an alien twist. Among the chemical lines was a molecule so extraordinary it electrified the scientific community: dimethyl sulfide, DMS. On Earth, this compound is produced exclusively by life, mainly by plankton drifting in our oceans. It is unstable, breaking down quickly in the atmosphere, meaning its presence is proof of an active, living biosphere. Even more compelling, Webb's readings showed DMS spread throughout the planet's atmosphere, suggesting that life here is not limited to isolated niches, but is woven into the entire planetary system. High levels of hydrogen and methane hint that these organisms might run on biochemical engines utterly alien to us, perhaps metabolizing gases in ways life on Earth never evolved to do. Detecting such delicate signatures is a triumph of precision. Webb had to measure starlight absorption with an accuracy of 1 part in a million, teasing out signals fainter than a whisper in a stadium full of noise. Yet in that faint whisper was the voice of another living world. And K2-18b is not alone. Just a few light years away, another system, CE Antel, tells a different but equally stunning story. At just 6.4 million years old, this red dwarf star is in cosmic infancy, still swaddled in the debris disk from which planets are being born. Its youth is violent. Colossal flares erupt without warning, bombarding newborn worlds with radiation fierce enough to strip atmospheres bare. Yet, one planet here, orbiting in the middle debris ring at a temperate 120 degrees, not only survived these tantrums, but appears to be actively sculpting its surroundings. The disk is split into 3 distinct rings, an inner band of fine dust, and rock slowly fusing into planetesimals, a middle zone, where the new planet's gravity sweeps up ice and stone, carving the very gap in which it resides. An outer halo of untouched, pristine material, the raw ingredients for future worlds. We are watching not just a planet, but a planetary architect, shaping the architecture of its system, while perhaps, just perhaps, preparing the conditions for life to someday take root. The planet is still in its infancy, a newborn in cosmic terms, yet it is already locked in a furious struggle for survival and dominance. Its growing gravity acts like an invisible net, pulling in rocky fragments, icy shards, and streams of interstellar dust from the swirling debris disk around it. With every impact, the planet gains not only mass, but also heat. Tremendous heat. Each collision releases a burst of energy, powerful, enough to melt rock, vaporize ice, and briefly turn entire regions of its surface into oceans of magma. This violent bombardment, far from being destructive alone, may be the very process that sets the stage for life. Geologists on Earth have long theorized that such cataclysms are crucibles for complexity. When mineral-rich meteorites slam into a young planet, they deliver exotic elements, phosphorus, carbon, nitrogen, that become the raw ingredients of biochemistry. Combine these elements with the immense pressures generated by impact shock waves, and you create the perfect laboratory for forging complex molecules that may one day assemble into living systems. But the planet's transformation doesn't rely solely on collisions. The nearby young star floods the system with ultraviolet radiation, an invisible but relentless sculptor of atmospheres. Each high-energy photon that strikes the planet's gases can shatter a molecule into fragments, radicals, and ions that quickly recombine into entirely new compounds. Among these could be organic molecules, amino acids, hydrocarbons, or precursors to nucleic acids. In essence, the star's fierce light may be sowing the seeds of chemistry that billions of years later could bloom into biology. More astonishing still, the planet is not simply a passive recipient of its environment, it is actively shaping it. Its gravitational influence acts like a cosmic chisel, carving an exquisitely defined gap in the debris disk. Instead of a chaotic spread of dust and rock, the space around its orbit is unnaturally clean, as though swept by an unseen broom. This is not a random feature. It's the unmistakable signature of a planet exerting long-term control over its neighborhood, sculpting the very architecture of its system. Early telescopes on Earth caught only the broad outlines, rings of material, a conspicuous void, but they could not explain how such precision was possible. Alternative theories invoked magnetic anomalies or random collisional clearings, but none matched the observed perfection of the gap. It took the James Webb Space Telescope, with its unparalleled infrared sensitivity, to cut through the mystery. Its detectors picked up the faint glow of a warm, young world hidden in the void, a planet still radiating the residual heat of formation. This Saturn-mass giant orbits much closer to its star than Saturn does to our Sun, yet its gravitational reach is powerful enough to maintain the gap's clean edges year after year, century after century. Simulations now confirm what the data implies. The planet's orbit creates resonant zones, safe harbors where debris can collect without destabilizing. These zones correspond exactly to the ring structures seen in Webb's images, a match too precise to be coincidence. And the contents of those resonant rings are intriguing. Observations suggest they hold water-rich comets, icy asteroids, and carbon-heavy dust. Precisely the kind of material that, if drawn inward, could one day feed the growth of an atmosphere. Over eons, such imports could layer the planet with volatile compounds, transforming it from a sterile giant into a potentially habitable world. Perhaps most tantalizing is its steady, almost uncanny surface temperature. 120 degrees. This figure is neither scorching enough to sterilize life's fragile chemistry, nor cool enough to halt the complex reactions life requires. Instead, it sits in a rare sweet spot. On Earth, ecosystems around hydrothermal vents thrive in similar conditions, using the constant heat to drive metabolism without sunlight. Laboratory experiments add weight to the coincidence. Around 120 degrees, amino acids, the molecules that knit together into proteins, form with remarkable speed and stability. Water remains liquid, nutrients dissolve readily, and chemical reactions proceed at an accelerated yet sustainable pace. It's as if the universe has dialed this planet's thermostat to the ideal setting for life's first spark. This world, hidden in a dusty ring 124 light-years away, is more than just another point of light in a telescope. It is an active participant in its own creation, architect, chemist, and perhaps, one day, cradle of life. If life can begin here, in the heart of such chaos, then the galaxy may be filled with worlds where creation is not a gentle process, but a violent, beautiful struggle that shapes life itself. This temperature range is not merely a comfortable zone. It is a cosmic alchemy point. At roughly 120 degrees Fahrenheit, molecular building blocks are free to dance, collide, and bond in ways that colder worlds cannot sustain, yet without the destructive chaos that higher temperatures unleash. It is here, in this sweet spot, that chemical reactions proceed at rates conducive to life, creating the amino acids, sugars, and lipids that form the scaffolding of biology. Too cold, and reactions grind to a near halt, as if the universe presses the pause button. Too hot, and fragile bonds shatter, leaving behind molecular rubble. What's astonishing is that multiple planets, separated by light years, orbiting entirely different types of stars, seem to have arrived at this same thermal balance. Yet they do so through entirely different mechanisms. Some achieve it through greenhouse effects far more potent than anything seen on Earth, where thick envelopes of hydrogen or carbon dioxide trap stellar warmth like an enormous planetary blanket. Others owe their heat to deep planetary interiors, where the decay of radioactive elements or the relentless crushing force of gravitational compression generates a steady, invisible warmth. A few appear to combine both, crafting climates of uncanny stability that may have persisted for eons. The pattern hints at something deeper, a universal preference for this temperature, as if nature has discovered its own recipe for life's maximum potential. In the same way stars have preferred sizes and masses that let them burn steadily for billions of years, planets might have preferred climates that let life not merely survive, but evolve into dazzling complexity. This thermal harmony could be the cosmic stage upon which biology performs its grandest symphonies. Even more compelling is the possibility that such warmth actively drives evolution forward. Higher metabolic rates, faster reproduction cycles, and increased mutation frequencies all accelerate the branching of life's evolutionary tree. In these worlds, life would not crawl toward complexity, it would sprint. Meanwhile, the stability of this climate prevents the catastrophic swings that can erase entire ecosystems. Such planets might give rise to biospheres so diverse and intricate that even Earth in all its beauty would seem simple by comparison. The discovery of multiple such worlds raises a tantalizing question. Is this temperature sweet spot a random coincidence, or is it a fingerprint of a universe fine-tuned for life? Could it be that life is not a rare accident, but an inevitable outcome wherever the right conditions emerge? One such world, K2-18b, takes this idea and thrusts it into the realm of active mystery. Among the many gases detected in its hydrogen-rich atmosphere, one stands out: methane. Methane should not be there, not in the quantities observed. This simple molecule, with its single carbon atom embraced by 4 hydrogens, is fragile under stellar light. Ultraviolet radiation should break it apart quickly. Without a constant source replenishing it, methane should vanish in short order. Yet the James Webb Space Telescope, JWST, sees it clearly and in surprisingly high concentrations. On Earth, methane is almost always the product of life. Wetland bacteria exhale it as they digest organic matter in oxygen-deprived waters. Microbes in the guts of animals, from cows to termites, produce it as a metabolic byproduct. Even certain plants quietly release it. But while the sources vary, they share a unifying truth. They are all biological. Geological processes can make methane, but in quantities so small they cannot account for what Webb has detected on K2-18b. The implication is staggering. K2-18b may not just harbor life. It may host life so active, so prolific, that it shapes the entire atmosphere. Methane levels appear to be orders of magnitude higher than what geology alone could sustain, pointing toward a biosphere far more productive than Earth's. But the intrigue runs deeper still. In K2-18b's exotic atmosphere, methane might play a role unlike anything we see here. It could be both a carbon source and an energy source, supporting entire ecosystems that breathe methane and metabolize it as fuel. The planet's chemistry might allow life to exist in forms we've never imagined, perhaps with biochemistries alien to Earth, yet perfectly adapted to their world. Laboratory studies here on Earth have shown that under certain conditions, methane and hydrogen can combine to form amino acids, the raw ingredients for proteins, and thus for life. On K2-18b, the entire atmosphere might function as a planetary-scale chemistry lab, tirelessly churning out the building blocks of biology. The persistence of methane also tells a story of time, of continuity. It suggests that whatever is producing, it has been doing so for millions, perhaps billions of years. That in turn implies that the planet's climate and atmosphere have remained stable enough to support life over geological epochs, giving evolution the chance to push life toward ever greater complexity. And perhaps methane is just the tip of the iceberg. K2-18b's skies may contain a cocktail of interacting gases, each supporting a different form of metabolism. Imagine an atmosphere where multiple ecosystems stack in layers, from the surface to the edge of space, some organisms feeding on methane, others on hydrogen, and perhaps others on compounds we have yet to recognize as life's fuel. This would not be an atmosphere in the traditional sense, but a planetary superorganism, a living, breathing entity whose every molecule plays a role in sustaining its biosphere. The methane mystery is therefore not simply a chemical curiosity. It's a window into an alien world where life and atmosphere have evolved together into a single integrated system. And the fact that we've detected it at all is a testament to the power of JWST, which is only at the beginning of its mission. The next step is the Biosignature Survey, an ambitious, unprecedented sweep of the stars. Astronomers will target over 200 nearby star systems within 100 light-years, scanning every potentially habitable planet for the chemical fingerprints of life. This will not just be a list of possible worlds, it will be the first real catalog of life in our corner of the galaxy. Webb's upcoming tools will be able to read atmospheres more subtly than ever before, detecting faint biosignatures even from small, rocky planets. It will also be able to examine worlds that do not transit, planets we previously could not analyze because they never pass between us and their star. Advanced algorithms will search for complex molecular patterns, not just looking for Earth-like life, but for alien forms built on entirely different chemistries. Even more intriguingly, scientists will watch how planetary atmospheres change over time. By observing them for months or years, they can detect seasonal cycles, chemical pulses, or long-term shifts, signs not just of life existing, but of life responding to its world. This is no longer a question of if we will find living worlds. It is a question of how many and how soon. On Earth, the changing of seasons isn't just a shift in weather, it's a planetary pulse. Our atmosphere subtly breathes in rhythm with life. Plants absorb carbon dioxide in the summer and release it in the winter. Plankton blooms alter. Oxygen levels in the oceans and countless biological cycles adjust in harmony with the tilt of our planet. These seasonal fingerprints are so distinct that they can be measured from space. Now imagine detecting such variations on a distant exoplanet. The same rhythmic rise and fall of atmospheric gases, perfectly timed to that planet's own seasonal clock. It wouldn't just suggest the presence of life. It would hint at an active, evolving biosphere, one that responds to its environment in real time, perhaps even echoing the complexity of Earth's own systems. In the upcoming observation campaign, this will be one of the Webb Space Telescope's most exciting targets, the search for seasonal biosignatures. But Webb's mission isn't stopping at signs of biology. It's also reaching for the far more elusive prize, technosignatures. These are the chemical and electromagnetic whispers of a civilization capable of shaping its own planet. On Earth, our industrial age has left a detectable atmospheric mark. Compounds like chlorofluorocarbons, CFCs, and nitrogen dioxide that don't occur naturally in large quantities. If such artificial gases were detected in the atmosphere of a distant world, the implications would be staggering. We would be looking at the first direct evidence of an alien technological civilization. To make this possible, the campaign will work in perfect coordination with other observatories across the globe and in orbit. Giant radio telescopes will quietly listen for narrow-band transmissions, unnatural signals that could only be produced by deliberate engineering, from the same star systems where Webb detects biological or chemical anomalies. Meanwhile, powerful ground-based optical telescopes will scan those worlds' dark hemispheres, looking for the faint glimmer of artificial night-side illumination, perhaps the alien equivalent of cities glowing in the dark. This multi-wavelength strategy is unprecedented in human history. Each observing platform will act like a different sense. Webb's infrared vision for heat and chemistry, radio arrays for structured transmissions, optical instruments for direct visual anomalies. Together, they will weave the most ambitious and thorough search for extraterrestrial life and intelligence ever undertaken. And the tools are only getting sharper. The next generation of coronagraphs will allow Webb and its successors to block out more of a star's glare, making it possible to see Earth-sized planets in orbits closer to their suns. New spectrographs will sharpen atmospheric readings to the point where trace gases, the ones that today hover just below our detection threshold, could finally be measured. At the same time, advances in AI-driven image processing will allow astronomers to extract faint planetary signals from raw data that would once have been dismissed as noise. But this campaign is about more than instruments. It's about intent. This is humanity's first systematic effort to map where life exists in our galaxy, not just by guessing, but by actually identifying and cataloging alien worlds with biological or technological fingerprints. If the timeline holds within the next decade, we could have a list of hundreds of confirmed living planets, each with its own atmospheric personality and evolutionary backstory. And if the patterns we're beginning to suspect are true, the universe may turn out to be not sparsely inhabited, but teeming, which leads to the ultimate question, the question that has haunted humanity for centuries. Are we alone? In the eye-by face of this coordinated, multi-pronged search, the answer may come back not as a whisper, but as a cosmic chorus. No, and we've been surrounded by company all along. The three-ring story of CE Antilla Nowhere is the artistry of planet-making. More vividly on display than in the CE Antille system, a young star surrounded by a magnificent debris disk. Astronomers liken it to a cosmic three-ring circus, each ring a different act in the grand performance of planetary birth. These aren't chaotic clouds of dust. They are organized, structured layers, each with its own unique role in the drama of world formation. The innermost ring hugs the star at blistering proximity, so close that temperatures could melt lead. Here, the dust is fine, the particles tiny, yet they remain in stable orbits. Every collision between these grains is a rehearsal for something larger. Each impact sticks matter together, producing ever bigger clumps that will one day serve as the seeds of rocky planets. In the middle ring, where Webb recently detected a new planet, the environment is a delicate balance of rock and ice. This is the sweet spot for complexity, a zone where both solid minerals and frozen volatiles coexist. The discovered planet here has already swept much of the debris from its orbit, a sign that it's been growing steadily, but the remaining material still bears the fingerprints of active accretion. This middle zone is where habitable conditions could potentially emerge, should the right combination of chemistry and stability occur. The outermost ring is the freezer of the system, a pristine reservoir of ice, organic compounds, and untouched material left over from the star's formation. This is the storage vault of planetary ingredients, waiting to be delivered inward by the gravitational nudges of larger bodies or the random chaos of collisions. Many scientists believe such icy imports may have been the source of Earth's own oceans and possibly its first building blocks for life. What makes CE Antilla's rings truly remarkable is their precision. They are not scattered at random, but spaced according to the laws of orbital resonance, the gravitational dance steps that dictate where stable zones can exist. The clean gaps between them mark areas where gravitational disturbances, often from forming planets, keep material from settling. Computer simulations show that these rings are not frozen in time. Material from the outer ring slowly drifts inward, feeding the growth of planets in the middle and inner zones. The newly discovered planet acts as both a builder and a gatekeeper, preventing too much material from flooding the inner system. Too quickly, allowing worlds to grow steadily rather than chaotically. And in the middle of all this artistry lies Webb's newest prize, a planet that has rewritten the record books. With a mass just 1/3 that of Jupiter, it is the lightest planet ever directly imaged around another star. In the past, direct imaging of exoplanets was limited to massive super-Jupiters, so large and hot that their glow was easy to pick out from the glare of their stars. But this new world, 10 times less massive than any directly imaged before, is fainter, cooler, and far harder to detect. Its light is nearly 10 billion times dimmer than its parent star, requiring Webb to operate at the absolute edge of its sensitivity. That it succeeded is not just a scientific breakthrough, but a triumph of human engineering and ingenuity. And while its low mass makes it an observational challenge, it also makes it a treasure for science, a possible bridge between the massive gas giants and the smaller, potentially habitable terrestrial planets we most hope to find. Objects with masses similar to Jupiter occupy a fascinating threshold in planetary science, a frontier where worlds straddle the boundary between colossal gas giants and smaller, rocky terrestrial planets. For decades, astronomers have theorized about what lies in this transitional zone. Now, this newly imaged planet sits squarely on that frontier, offering a rare window into how planetary systems evolve and how nature decides which worlds become turbulent spheres of hydrogen and helium and which solidify into smaller, rocky havens that could one day host life. Understanding this boundary isn't just an academic exercise. It is one of the keys to predicting where habitable planets might form. Gas giants like Jupiter, with their immense gravity and thick atmospheres, shape the architecture of entire planetary systems. They can shepherd asteroids, redirect comets, and protect inner worlds from destructive impacts, or in some cases destabilize or eject them entirely. This planet's position at the boundary suggests it may share characteristics of both categories. Large enough to retain a substantial atmosphere, but possibly light enough to allow a solid core to exist beneath it. And here lies the intrigue. While most Jupiter-mass planets have no solid surface and are entirely inhospitable to life as we know it, this lighter cousin may possess a dense, rocky, or icy interior wrapped in a relatively thin veil of gases. Its surface temperature, hovering around 120 degrees, 49 degrees, hints at a carefully balanced atmosphere, one thick enough to trap warmth via the greenhouse effect, but not so massive that it balloons into an uninhabitable gas giant. Detecting such a low-mass, faintly glowing world pushed the James Webb Space Telescope's technology to its absolute limits. Its infrared instruments had to pick out the planet's delicate thermal signature from a backdrop dominated by the blinding light of the host star and the shimmering dust of the surrounding debris disk. The process required innovative observational strategies, capturing multiple exposures at different wavelengths, subtracting background signals, and then applying state-of-the-art image processing algorithms that systematically stripped away the contaminating light. In essence, Webb scientists extracted the faint murmur of a planet's heat from the deafening roar of starlight, a whisper teased from a cosmic thunderstorm. The planet's low mass makes it more than just a curiosity. It makes it a perfect laboratory for atmospheric exploration. Thick, crushing atmospheres on massive worlds can conceal their lower layers from even the most advanced telescopes, masking the very chemical interactions that might hint at life. But here, the relatively thin envelope of gases invites Webb to peer deep within, potentially revealing a tapestry of atmospheric chemistry in fine detail. And perhaps most importantly, this detection proves something profound. Webb is capable of finding and studying planets that genuinely mirror the scale and nature of those in our own solar system. The pathway to discovering and characterizing truly Earth-like worlds, worlds with oceans, clouds, and maybe even continents, has now been illuminated. The discovery of this faint, low-mass planet marks more than a technical achievement. It marks the opening chapter in what could be a golden age of the search for life beyond Earth. Over the next 2 decades, a new generation of telescopes, both in space and on the ground, will expand our reach into the galaxy with unprecedented sensitivity. Some of these instruments will dwarf Webb's capabilities, targeting not only exoplanets, but the elusive signs of biological activity itself. The most ambitious of these is NASA's planned Habitable Worlds Observatory, a space-based marvel designed specifically to detect and analyze Earth-like planets orbiting Sun-like stars. Armed with cutting-edge coronagraph technology capable of achieving contrast ratios of 10 billion to 1, it will be able to directly photograph pale blue dots like our own, even against the glare of their parent stars. More than just images, it will dissect the starlight passing through these worlds' atmospheres, searching for unmistakable chemical fingerprints, oxygen, water vapor, methane, and other potential biosignatures. On Earth, massive ground-based telescopes are preparing to join the hunt. Chief among them is the extremely large telescope in Chile, currently under construction, with a primary mirror stretching over 100 feet, nearly 5 times larger than Webb's. This behemoth will allow astronomers to study the atmospheres of nearby exoplanets in exquisite detail, picking out dozens of molecules that might signal life, industry, or entirely alien chemistries. But finding life is not only a matter of building bigger eyes. The sheer flood of data these instruments will generate demands something more, an intelligence capable of spotting patterns invisible to the human mind. Artificial intelligence and machine learning systems are already being trained to sift through oceans of spectral data, recognizing subtle signs of chemical disequilibrium that no human analyst could detect unaided. Such patterns might betray life forms utterly unlike anything on Earth, life that breathes not oxygen, but perhaps exotic gases like sulfur hexafluoride or ammonia. This shift in thinking has given rise to a revolutionary approach: the search for agnostic biosignatures, chemical signals that indicate life without making assumptions about its form or metabolism. Instead of looking for familiar markers like oxygen or chlorophyll, astronomers will search for signs of active chemical cycles that no known geological or physical process could maintain. Even more tantalizing is the possibility of real-time life detection. In the near future, observatories may be able to track minute-to-minute changes in an exoplanet's atmosphere, perhaps watching the daily breath of a living biosphere as it exhales oxygen in daylight and consumes it at night, or as it shifts with seasonal cycles. And beyond biology lies an even greater leap: the search for technology itself. The same instruments that will detect alien life could, in principle, detect alien civilization, traces of atmospheric pollution, patterns of artificial lighting on a planet's night side, even the waste heat of vast power-generating structures. The search for extraterrestrial intelligence, SETI, will merge seamlessly with exoplanet science, making the detection of advanced life not an extraordinary mission, but a routine step in planetary characterization. Within 2 decades, we may catalog hundreds, perhaps thousands of living worlds, each with its own story written in the chemistry of its skies. The galaxy, once thought to be a lonely expanse, may reveal itself as a vast, humming network of biospheres, some simple, some unimaginably complex, and some perhaps as curious about us as we are about them. The decisive moment, when it comes, will likely arrive without grand announcement. Somewhere, perhaps in a quiet laboratory, a scientist will lean over a monitor and notice the unmistakable signal in a planet's spectrum, a pattern that cannot be explained by geology, chemistry, or physics alone. It will be life. And in that instant, the centuries-old question, "Are we alone?" will be answered with a definitive, world-changing no. Already, the discovery of potential biosignatures on K2-18b has brought us to the very threshold of this moment. The dimethyl sulfide in its skies, the interplay of methane and hydrogen, the chemical disequilibrium that only biology could maintain, all point toward a thriving biosphere 124 light-years from Earth. Statistically, the case is strong, 99.7% certainty, but science demands more. The moment of absolute certainty will come when multiple observatories, using different methods, confirm the same signals beyond any shadow of doubt. When that day comes, the announcement will not just rewrite astronomy, it will rewrite history, philosophy, and humanity's understanding of its place in the cosmos. Science will be revolutionized, not merely adjusted, as we grapple with the undeniable truth that biology is not an earthbound anomaly, but a universal principle, a phenomenon written into the very physics and chemistry of the cosmos. Our philosophies will be reborn, reshaped under the weight of this new reality. Every religion, every belief system that has ever wondered about the heavens will be confronted with an awe-inspiring revelation. The human story was never solitary. Our place in the grand architecture of existence will have to be redrawn, not as a lonely beacon in the dark, but as one star in a vast constellation of life. Technology will accelerate beyond anything we've yet experienced, driven by a hunger to explore, to reach out, and perhaps one day to communicate across the abyss of space. And the psychological shift, the way we see ourselves, will be profound and irreversible. The knowledge that we are not alone will sweep away the cosmic isolation that has haunted our species for tens of thousands of years. No longer will our night skies seem like silent, indifferent voids. We will know that behind some of those distant points of light, something is looking back. The moment we confirm life elsewhere will make us members, however distant, however new, of a galactic community. Each world, each biosphere, following its own path of evolution, yet bound to us by the shared miracle of existence. But with this knowledge will come responsibility. The more living worlds we find, the more urgent our moral questions will become. What are our obligations to life beyond Earth? How do we explore without exploiting? Can we protect what we have not yet touched? We will need new ethical frameworks, new philosophies of stewardship that extend not only across borders and oceans, but across star systems. The discovery of extraterrestrial life will demand that we see ourselves not just as Earthlings, but as caretakers of life wherever it emerges. The day we are no longer alone will be remembered as the beginning of humanity's greatest chapter. We will transition from a species that wonders to a civilization that knows. The universe will no longer be a vast emptiness dotted with rare sparks. It will be a living ocean, teeming with ecosystems and experiments in biology beyond anything our planet has ever known. And when we look back, we will see that the turning point began here, with the James Webb Space Telescope's first detection of biosignatures on K2-18b, 124 light-years away. Those faint chemical whispers, dimethyl sulfide in the atmosphere, of a warm, hydrogen-wrapped world, will be remembered as the first proof that ended our cosmic solitude. This was the evidence that shattered the silence, and as we've learned more, we've seen that K2-18b is not an outlier. Webb has shown us that habitable worlds may be scattered everywhere, each sculpted by its star, each carrying the possibility of life. From planets still forming in swirling disks of dust to ancient worlds orbiting long-lived red dwarfs, the galaxy may be filled with places where life not only survives, but thrives. This truth changes everything. Our sciences will adapt, our cultures will evolve, and our dreams will grow larger than any horizon we've ever known. Future telescopes will not just confirm a handful of living worlds, they will reveal hundreds, perhaps thousands, each with unique chemistries, climates, and evolutionary stories. We may find life that shares none of our building blocks, life that breathes alien air, swims in alien oceans, and thinks alien thoughts. And in doing so, we will expand our definition of what it means to be alive. For the children born after that day, the knowledge will be as natural as sunlight. Life exists everywhere. They will grow up understanding that the galaxy is a community, and that humanity is one voice in a much larger chorus. This will not only inspire our sciences, but reshape our art, our literature, and our very sense of purpose. And perhaps the most humbling truth of all will be this: life is not rare. It is inevitable. Wherever conditions permit, it blooms. It transforms barren rock into living landscapes, silent atmospheres into breath and song. The signatures detected by Webb are more than data points. They are the first clear evidence that the universe itself is, in some deep and poetic sense, alive. The James Webb Space Telescope has lifted the veil, offering our first true glimpse of our cosmic neighborhood. We will no longer think of ourselves as a fragile accident in an indifferent void, but as part of a vast interwoven tapestry of biology that stretches from one end of the galaxy to the other. We were never alone. We never have been. The universe has been quietly alive for eons, simply waiting for us to open our eyes. Now, we stand at the threshold of this new reality. A cosmos, breathing with the rhythm of countless worlds, invites us forward, and as we take that step, we carry with us a truth that will echo through all of human history. The universe is alive, and we are part of its story.